Everybody, this is lecture 33, Wednesday the 15th of April. We're covering section 9.2, calculus of parametric curves, second day discussing this topic. So remember, a parametric curve is one where you're given x and y coordinates that are functions of some other variable, some parameter. We've been thinking of the parameter as t for time. So in section 9.1, we just discussed parametric curves. We visualize them. On Monday, we started this topic of calculus with parametric curves. So we talked about tangents to parametric curves. So that involves calculus, finding derivatives. And we talked about areas enclosed by parametric curves in the x-axis. So that also involved calculus, involved integrals. So today, we're talking about lengths of parametric curves. So length of a parametric curve. Now I'm going to start with a theorem it's kind of an ugly looking thing, and the book spends about a page and a half, which is a lot of real estate in a book, trying to develop this, developing this theorem. So I'm not going to do that in lecture. It would be a terrible thing to do in lecture. But this is a theorem. So this is the length of a parametric curve. So if curve C is described as x of t comma y of t. So again, there's the idea of a parametric curve. Its coordinates are given by functions. For t, and here I'm going to use highbrow Greek letters, alpha and beta. So that's the if, but the if is not done. And the curve does not retrace its steps. So the curve is traversed exactly once as t goes from alpha to beta. And there's more. X prime of t and y prime of t, so these derivatives, exist and they have to be continuous. So that's a whole lot of ifs. If all that stuff is true, then the length of C is this, capital L obtained by this integral from t equals alpha to beta of this crazy square root thing, x prime of t squared. So that's the derivative. That's not an exponent. That's x prime plus y prime of t squared. Again, that's a prime, dt. So I'm not going to go over why this is the formula. If I have time at the end of the hour, which I never do, I'll try to make my stab at it. So what I want to do is some examples. So example 1. Find the exact length of the curve 1 plus 3t squared, comma, 4 plus 2t cubed for t between 0 and 1. All right, so we would like to use that horrible formula. But look, we've got a whole bunch of ifs. First of all, do the derivatives exist? So x prime of t, that's going to be d dt of 1 plus 3t squared and so that's 6t. And that exists, and it's continuous. Okay, what about y prime of t? Well, that's going to be the derivative of 4 plus 2t cubed. What's that derivative? Marcy?
6t squared.
6t squared. So that exists. It's continuous. Great. What else do we need to check? Marcy?
The curve is traversed exactly once as t goes from A to B.
Yeah. In other words, does the curve retrace its steps? Now this can be tricky because, I mean, this problem is not asking us to make a picture of this curve. That would be a substantial problem just by itself. We've done problems like that on Friday, or last Wednesday, and then again this past Monday. But I'd like to avoid that. Now, a curve retracing its steps can happen a couple of different ways. Something like this would be okay. That curve doesn't retrace itself. Something like this would be okay. The curve intersects itself, but it doesn't retrace its steps. Something like this, though, not okay. So we want to see if this happens. This can be hard to figure out, but this can actually be easy to figure out. Now notice that if the curve retraces its steps, then there's going to be some point on the curve that appears at more than one time value. Here there's exactly one point on this curve that appears twice. Here there's going to be a whole bunch of them. But let's just see, are there any points on this curve that appear at more than one time value? So any points that occur at more than one time value. If there are, then we'd have to do some more checking. It could be this, in that case would be okay. It could be this, in that case we're not okay. The curve would be retracing itself. So look at this formula. Anybody have any wisdom about that? Are there any? Can you think of arguing about these formulas? Let's look at the x-coordinate. Well, we'll just observe. T cubed is an increasing function. That is, it looks like this. So increasing in the sense that if T1 is less than T2, then T1 cubed is less than T2 cubed. So look at our formula. Our y-coordinate is y is 4 plus 2t cubed. That's also going to be an increasing function. So if t1 is less than t2, then y at time 1 is going to be less than y at time 2. So there aren't going to be two different time values where the resulting point has the same y-coordinate. So no two points on the curve will have the same y-coordinate. Okay, so the curve never intersects itself at all. We don't have this. We certainly don't have this. So that's a fair bit of work that we've done. We've just been checking the requirements. Okay, so now we're going to get to work and compute the length So we're going to use that formula to get L. So L is going to be the integral from t equals 0 to 1 of the square root of, now I'm going to save some time here. I'm going to have x prime squared. Okay, x prime is already over here. X prime is just 6t. So I'm using that formula. So I have 6t squared plus 6t squared squared. So let's get to work cleaning this up. This is the integral from 0 to 1 of the square root of, this is going to be 36t squared plus 36t to the 4th dt. Let's factor out a 36t squared. So then I have 1 plus t squared dt. I'd like to pull that 36t squared out. When I pull that out, what do I have to write here? Let me give you a hint. On the count of 3, everybody tell me, square root of x squared is?
X.
Wrong. Absolute value of x. This means the non-negative square root. If x is 5, then x squared is 25, square root of x squared is 5, so x squared of x squared is x. But if x is negative 5, the square root of x squared is not negative 5, it's plus 5. So when you pull something out of the square root, it's got to be non-negative. So this is going to be 6 times the absolute value of t. Now, think about that. Do we have to have that absolute value? Trent, why not?
T's from 0 to 1.
Exactly. So now, once it's out, we can look at it and realize that we know that t is greater than or equal to 0, so then we can just write this as 6t. But you got to go through the motions. You got to acknowledge that that's an issue and make sure that you address it. Okay, now we're going to do a substitution. So we're going to let 1 plus t squared equals u, and then we're going to go through all the steps, and that's a Calc 1 problem. So here we have the integral from t equals 0 to t equals 1. After we do the substitution, we get this. We get the integral from u equals 1 to 2 with a 3 in front and u to the 1/2 du. So again, this is a standard substitution problem. You go through the steps. You've got to figure out a new version of dt. You've got to transform the limits of integration. So this is going to be 3 times u to the 3/2 over 3/2, evaluated from u equals 1 to 2. Now 3 divided by 3/2, I flip that over and multiply, so I end up with 2 times 2 to the 3/2 minus 1 to the 3/2. So I end up with 2 times 2 square root of 2 minus 1. And there's my length. So not a terribly hard integral, except that you got to do the substitution. Excuse me. Okay, example 2. We have 3 very different kinds of examples today. Find the exact length of this. E to the t cos t times e to, comma, e to the t sine t for t going from 0 to 4 pi. Okay, well, look, we know we're going to need to have x prime. So let's look at x prime. X prime of t, that's the derivative of that thing, e to the t cos t. And I have to use the product rule. So I'm going to take the derivative of the first, that's e to the t, times the second, that's cos t, plus the first, that's e to the t, times the second, that's minus sine t. And I can factor that out. So this is x prime of t. It's going to be e to the t times cos t minus sine t. And notice this exists and it's continuous. Okay, let's look at the derivative of y. Y prime of t, that's going to be the derivative of e to the t sine t. Well, so again, this is going to be a product rule. And you can see that when I'm done, I'm going to, I think it's believable that I'm going to have e to the t times the quantity sine t in this case, plus cos t, because this was the result of taking the derivative of cosine. I get the minus. This is the result of taking the derivative of sine. I don't get a minus. And so notice that this exists, and this is continuous. So those first two prerequisites are fairly easy to check. You just find the derivative, see if the derivatives exist, and see if they're continuous. But the third requirement is always more tricky. Does the curve retrace itself? Anybody have any wisdom about that? Does this curve ever retrace itself? Jace?
Could be wrong, but I feel like it's going to end up being a circle.
Marcy?
I feel like it's going to end up retracing itself because it's an alternating function.
Alternating means, you mean periodic?
So E of t is always going to be positive and increasing, but cos of t is going to be periodic, so is it going to be a spiral?
Say it a little louder. Everybody listen to this.
E of t is always going to be a positive and increasing number, and cos of t is going to be periodic, so it'll spiral out.
Yeah. So if this were this curve, cos t and sine t for 0 less than or equal to t less than or equal to 4 pi, that would be this. So this would be at t equals 0, and also again at t equals 2 pi, and also again at t equals 4 pi. Goes around twice. And notice an object on this circle, what's the radius? 1, because sine squared plus cos squared equals 1. Our curve is e to the t cos, e to the t sine for t between 0 and 4. Okay, so it's going to start at the same point. This is the point 1 comma 0. And that's the radius there is a distance 1. But as it goes around, it becomes farther and farther from the center. So what is the radius for a point on this? What's the distance from the center for a point on this curve? Marcy? Say it again? Yeah. R equals e to the t. Because if you take x squared plus y squared, you get e to the t squared times cosine squared t plus e to the t squared times sine squared t. This cos squared plus sine squared equals 1. So you end up with square root of e to the t squared. You just get e to the t. So this thing is always spiraling outward, so it never retraces its path. I think it's a really cool thing that you can generate. You know, think about how to brew up a spiral. Now you know. Think about something that's not a spiral, just a circle, pretty simple, and then just do anything that would make it grow. Can anybody think of something else that we could have done to make this thing a spiral, Marcy?
X, or you could just put like any constant increasing value as the coefficient.
Yeah, but not x, maybe like t.
Yeah.
Yeah, t cos t and t sine t, where we restrict t to be a positive number or non-negative number. Positive number. Okay, so our curve never retraces itself. It never retraces its steps. So we're ready to set up our integral. We're going to integrate from t equals 0 to t equals 4 pi. And we need to have our x prime squared. Now we've already got that. Our x prime is e to the t times cos t minus sine t. And that whole thing's got to be squared, plus e to the t times the quantity sine t plus cos t. That whole thing's got to be squared inside of a square root there. But look, each of these terms has an e to the t. It's being squared, so there's going to be an e to the t squared on both of these terms. So I can pull that out front. But when I pull out front, I have to have an absolute value around it. And then I have square root of what's left. Cos t minus sine t squared plus cos t plus sine t squared. All right, who can help me out with the absolute values? Andrew, your hand was up briefly. Can we simplify this?
On the e to the t?
Yeah. Liam?
E to the t is always positive.
Yeah, e to the t is always positive. So we don't have to deal with that. So we have integral from t equals 0 to 4 pi, and we can just write e to the t. And then, look, we're going to get cos squared minus 2 cos t sine t, and then we're going to end up with a sine t squared. That's the first term squared. And then the second term is going to be the same thing. We're going to have a cos t squared. And then we're going to have a plus 2 cos t sine t. And then we're going to have a plus sine squared t. And that's all going to be under the square root. And there's going to be a dt. Okay, so now look at this. I have a minus 2 cos t sine t there that cancels this plus 2 cos t sine t. Now, can anybody see anything else that can be simplified inside this square root? Let's get some new hands here. I've got cos squared plus sine squared plus cos squared plus sine squared. Can anybody think of how to simplify that? I'm going to only call on new hands here, so Annika.
Cosine squared plus sine squared is equal to 1.
Yeah, so these two things, they have a cosine party, sine party. These two things get together and they make the number 1. And so do these. So I end up with the integral from 0 to 4 pi of e to the t times square root of 2. And so that's square root of 2 times e to the t from 0 to 4 pi. So that's square root of 2 e to the 4 pi minus e to the 0. So that's square root of 2 times e to the 4 pi minus 1. So the integral is not so bad. What takes a lot more thought, and the integral did involve calculations, Nothing we did over here involved hard calculations, but involved some thinking to figure out that this thing does not retrace its steps. That requires some difficult thinking. Okay, example 3. An object moves with coordinates x of t, y of t equaling this. 5 sine squared t, comma, 5 cos squared t for t going from 0 to 7 pi over 2. Find A, the length of the curve, B, the distance traveled, and C, the displacement. Okay. Well, I'm going to sort of cut some corners here because I've got some experience. So check requirements. X prime, is X prime going to exist, and is it going to be continuous? Well, it will exist, and it will be continuous. Y prime will exist, and it will be continuous. Now the hard question, does this curve retrace its steps? Does the object retrace itself, its steps? Now, I mentioned, I mentioned a while ago, I'm going to skip some stuff because I've got some experience. So there's lots of things in math where, there are tricks that might not have occurred to you, that will occur to you, once you've seen them enough, they'll start to seem like they were your ideas, but they're not. What I'm going to talk about here was not originally my idea. I just saw this at some point. But I mentioned that you should start keeping an eye out for something that can happen in equations. Anytime you see this thing, you should realize that you can do something with it. Look at our coordinate functions. What do you notice about those coordinate functions? Marcy's got a hand up. I'd like to see some more hands up. Monica's got a hand up. Marcy?
They're always positive, but not always increasing.
Right, but that's not going to. I'm thinking about something we can use that can simplify our problem. Hanukkah?
They're similar to the function of a circle. We have an x squared and a y squared value.
Yeah, but they're squared, so yeah. Kenzie?
They're bound between 0 and 1, and anytime, like for example, cosine of t would be -1, cosine squared of t is going to be +1. So cosine squared of 0 is equal to cosine squared of pi, for example. And sine squared of 0 and sine squared of pi are also.
Even more basic than that. So here's where I get to, I get to sort of present myself as the grown-up in the room. But again, this was not my trick. I noticed, I was taught this at some point. So notice that x plus y equals what? 5, yeah, you already had it. You gave it away. You did, so it's 5 sine squared plus 5 cos squared. So that's 5 times the quantity sine squared plus cos squared. So that's just the number 5. So x plus y equals 5, so we get y equals 5 minus x. So that's a Cartesian description of the curve. It's not always possible, but that's cool because you really simplify your life by not having to think about t. So anytime you see a sine squared and a cosine squared kicking around, think about this. If I could throw a party and get them both in the same room, they're going to make the number 1. So again, that's the kind of thing. Keep an eye out in your mathematical and physics and whatever life. Talk about orbitals of things in quantum mechanics. There are lots of situations where you end up with a sine squared and a cos squared in the same room, and so they just equal 1. So what does this graph look like? I would like some more hands. There's a whole room full of people. All of you know this. William.
Just a line with a slope of -1 and a minor 75.
Good. So the particle lives on, or the object lives on that line. Seems like it never retraces its steps, right? But wait a minute, does it? These things are periodic. So we better figure out what's going on here. What's the first interesting time we should think about? Zero. Anybody have an idea for the first time we should think about?
0.
Good. What's the coordinates there? Let's get some hands in the air. So I'm not going to call on anybody who's called before. What's the x and what's the y at time 0? Yeah? 0, 5. So the coordinates of the point are 0, 5. What's the next interesting time that I should look at? Think about, you want to make your job easy. What's a time where you know how to compute this value really easily? Pi over 2. So somebody else, what are the coordinates for x and y there? 5, 0. So on my diagram, this is time equals 0, and by time pi over 2, the object has gotten down to here. Now, it's not retraced itself any time between then, because sine is growing from 0 to 1 during that time interval. What's the next interesting time that I should look at? Pi. What are the coordinates there? 0, 5. Aha! So the object does retrace itself, its steps. This is time 0, time pi. What's the next interesting time? 3 pi over 2. That's going to be back to 5, 0. So that's going to be 3 pi over 2. This is going to be at 2 pi. And then 7 pi over 2. So 1, 2, 3, 4, 5, 5 times the object goes across that same path. Okay, so let's answer these questions. What's the length of the curve? And then how far did the object travel? So I can draw the curve. There's the curve. What's the length of this? Not quite. Got to use Pythagorean theorem. Square root of 50, which is 5 square root of 2. Great. B, what's the distance traveled? Anthony, I think you have it, don't you? Well, how many times does it traverse this path? Liam, you had your hand up. 7 times, remember? Yeah, remember it goes 1, 2, 3, 4, oops, sorry, 5, wait. Oh, I didn't finish it. So this 5 pi over 2, and then 3 pi, and then 7 pi over 2. So 7 times. So the length is, distance is 7 times 5 square root of 2. So 35 square root of 2. Now, dun, 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 this is something new, something from the future. Now, I'm going to bring up something from Calc 1 that I think is going to lead you all to make the wrong answer, but it's going to make this more interesting. So, you know, here I am. This is the x-axis. That's the positive direction. This is time. This is position 0. So I'm going to walk over to here. This is 10 feet. I'm going to walk back. What's the length of that curve, Marcy?
Twice the distance you walked.
No. What's the length of the curve? If you look at my footsteps in the snow. No, I walked here, and then I backed up. You look at my footsteps in the snow, the length is 10. What's the distance that I traveled? 20. I walked there, and then I walked back. What's my displacement? 0. All right. So this So what's the displacement of this object? Liam?
5 pi over 2. Or sorry, 5 square root of 2.
That was the wrong answer I was hoping you would all make. So the displacement is a vector. So in one dimension, there's a difference between distance and displacement. Distance is always greater than or equal to 0. Displacement can be negative. I mean, here, my distance is 10. My displacement was negative 10. So in one dimension, displacement can be positive or negative or 0. Distance is always greater than or equal to 0. In higher dimensions, displacement is a vector thing. This object went over 5 and down 1. Displacement is a vector. The displacement vector. So that's not part of this course. That's why you should take Calc 3, because now you're all really curious and you're all mad because you had the wrong answer in mind. But it's really cool. You want to talk about displacement in general. It's the change in position. So in one dimension, change in position is a number. In 2 dimensions, change in position is a vector. Really cool. Isn't that cool? Yes, Mark, it's cool. All right. Example 4. Curve is x of t, y of t equals t minus e to the t, comma, t plus e to the t for -4 less than or equal to t, I'm sorry, -5 less than or equal to t less than or equal to 3. So A, set up integral to compute the length. Okay, we got to check the details. So x prime of t is going to be the derivative of that. So it's going to be 1 minus e to the t. So that exists, and it's continuous. Okay, what about y prime of t? Well, that's going to be 1 plus e to the t. That exists, and it's continuous. Now, does this object retrace its steps? Marcy,
No,
why?
because both equations are constantly increasing.
But they're not.
Oh,
But listen to what Marcy said and see if somebody can hop in and take it from Marcy's idea. Jace?
Y is always increasing.
Right. Y is made up of 2 increasing functions. So as t grows, y grows. So observe, again, this is why it's good to be in class, because you get somebody throws out an idea, and if it's not right, somebody else can fix it. And sort of learn from each other. So observe y of t equals t plus e to the t is always increasing. So there are no 2 points on the curve that have the same y value. So they definitely can't be 2 points on the curve that there aren't 2 times where the curve intersects. So it certainly can't retrace its steps. So curve never intersects itself, and certainly never retraces its steps. Okay, so I get L, I just get to do the integral. Integral from t equals -5 to 3 of the square root of this thing squared, 1 minus e to the t squared, plus 1 plus e to the t squared. Now, there's all sorts of math you could do to simplify this. But in the end, it's going to be an integral that, well, actually I think we do have the techniques to solve this integral, but it's really hard. So that's it for that part. B, use computer to get approximate value. Okay, so we're going to go to helpmecheatonmycalculus.com. And we're going to make the computer do all the work. So again, I'm not going to bother simplifying because the computer doesn't care about simplifying. So our function is 1 minus e to the t, right, squared, plus 1 plus e to the t, what have I forgotten? Square root of all that. All right, and then what are my time values? Oh, minus 5 to 3. There we go. Is that it? Go. Boom. Now look at this. You'll see why you're not asked in this problem to do the integral. Because that's the indefinite integral. It's a bear. And I don't even know if we've learned techniques that would do that. But let's just get the number, 35.0071. All right, now we have just a few minutes left. What I want to do now is question C. Find T4. Dun dun dun. Anybody know what that is? What were these things? Marcy? Okay, if you're not.
We were doing, there were estimations with like bar graphs that I don't remember the exact name.
Riemann sum.
Yeah, Riemann sums with either left rectangles or right rectangles or midpoint rectangles. What's the 4 telling you? How many rectangles? 4 rectangles. What's the T going to mean? Trapezoids. So recall for a trapezoid, we have width is delta x. And we have h1 and we have h2. And the area is going to be delta x times h1 plus h2 over 2. That's the formula for a trapezoid area. You take the average of the two parallel sides. So in other words, delta x over 2 times h1 plus h2. Well, so our integral is sitting on this real estate, minus 5 to 3. We got to have 4 rectangles. So minus 3, minus 1, 1, and 3. Those are going to be our rectangles. So we need to find the heights. This is going to be y at minus 5, y at minus 3, and so forth over to y at 3. So in our delta x is going to be 2. So our delta x over 2 is going to be the number 1. So our T4 is going to be 2 over 2. That's going to be the number 1. And then I've got to find the area of this trapezoid. So that's going to be y at minus 5 plus y of minus 3. And the divided by 2 has already happened. And then I've got to do y at minus 3 plus y at minus 1. And then I've got to do the next trapezoid, y at minus 1 plus y of 1. And then I've got to do the last trapezoid, y of 1 plus y of 3. Now look, a bunch of these things turn up more than once. There are 2 y of negative 3s. There are 2 y of negative 1s. There are 2 y of 1s, but there's only one of the ones on the end. So I end up with y of negative 5 plus y of negative 3 plus, 2 y of negative 3s plus 2 y of negative 1s plus y of 1, 2 of those, plus only 1 y of 3. Now I have to use the formula for the y values And here I'm gonna punt, and I'm gonna just have the computer do it. But the idea is you have a few enough rectangles that you should be able to compute these. So here's a help me cheatamacalculus.com, another site that they run, which is a trapezoid calculator. So there's our function, and I've typed in, oh, come on, get out of there. So I've set up the function, and I've given it the limits and the number of subintervals. How do you get rid of that damn thing? Okay, there we go. Ah! Oh my God.
Maybe you buy now for
Yeah, but can somebody just get out a credit card so we can get through this? All right, so when I go through this, I get 43.89. C. T4 is 43, and I've got exams to hand back, sorry. 43.8926. So that's not a very good approximation. So what the hell? Why bother with trapezoids? Well, watch this. Let's increase the number of trapezoids from 4 to maybe 200. If I use 200 trapezoids, look at that. 35.011. So much better. So what's the problem here? Why was T4 so bad? Well, it's because this graph has some really sharp turns. So that the trapezoid rule does not work well unless you have a lot of trapezoids. Okay, here we go. Sorry to keep you so close to the end. Alexandra.